last talk we talked about isotopes and gleaning information from the periodic table based upon the atomic number of protons, and number of electrons. But in reality, this type of writing, this type of symbols that we write for isotopes, iodine-131 or carbon-13, usually is very much focused only on one rare instance. Usually when we're discussing radioactive materials or isotopes, isotopic distributions. But be prepared to see it on this case. Now, more often than not, we don't concern ourselves with the number of protons or the number of neutrons in an element. Usually what we really care about is really the number of electrons. Or we're going to spend all this time, part of the semester, talking about how the individual properties of an element grow out of its electronic structure, not its nuclear structure. Part of the reason is the electrons are out here, and so that's where all the change takes place. Now, to deal with these chemical symbols, rather than seeing numbers in front of a chemical symbol, we're going to usually see numbers after a chemical symbol, and that means different things depending on where the numbers reside. More often than not, you will see elements written with numbers in the upper right-hand corner. This denotes charge. That's either a positive charge or a negative charge. Traditionally, we have a tendency to write it as a implied 1 when there's no charge. Sorry. I have a tendency to write it as an implied 1 when we're dealing with things that only are monovalent, have a plus or minus 1 charge. We don't actually write the 1, we just write a plus, or write a negative for negative. What this implies is that the material has gained 4 electrons. Remember, the central portion, the nucleus, the electrons are distributed around the outside. And so any changes that take place have to come from the electrons. If you start changing the protons, that changes the element. So charge is the sole provenance of the electrons. So it changes in the number of electrons. Now, of course, in chemistry's long tradition of confusing students, a carbon that has a -4 implies that it has gained 4 electrons. There's 4 extra negative charges. The sodium ion, on the other hand, Na+, this implies that it has lost 1 electron. So, gain or loss of electrons, they are the unit of charge that we're dealing with. So if you take away a bunch of electrons, you take away a bunch of charge, leaving behind a bunch of positive charges. So we can look at this chemical symbol and see that the carbon, which had 6 protons to begin with, and of course I was able to get that from my periodic table, to get that from the periodic table based upon the atomic number, it is gained 4 electrons, and so we could say that this thing now has 10 electrons. Why? Because it started with 6. Neutral carbon has 6 electrons, gains 4, so -4 charge to give us 10 electrons. So we should be able to relatively quickly figure out the number of electrons present in a system. So rather than talk about C -4, Na+, we usually start to use these names for these materials, and we'll talk about that. These materials are called ions. Right. Ions are elements or material or compounds that have gained or lost an electron. We say something has become ionized. We're going to spend most of the next 3 or 4 weeks talking about ionic materials. Materials that are composed of ions. Now, ionic materials are composed of ions, but almost always it's a positive ion compared with a negative ion. Something like Na plus and Cl minus. The problem is when you bring these two together to form compounds, the charge disappears because the overall charge on an ionic compound is 0. So we don't explicitly show it. It's implied, but it's not explicitly shown. Now, it turns out that compounds can be held together in many different ways. Now, compounds can exist as what we call molecules, groups of atoms held together by some sort of behavior that we call a bond. At least 2 atoms held together. Most materials that we deal with are groups of atoms, big, huge groups of atoms that are stuck together. Elements themselves can also exist as molecules. So these are molecular entities, 2 or more atoms held together. Atoms represent these little sticks, and so how they're held together is not quite as important at the moment. But the way we represent these, we can represent molecules held together using little symbols, subscripts they're called. So we can use the subscripts to talk about the elements. Now the subscript is immediately operating on the element next to it. So this would represent 2 H atoms bound in some fashion to 1 oxygen atom. Again, there's an implied 1. They're held together in some fashion. Now, we have other compounds, such as Na2SO4. Again, this would represent 2 sodium atoms, 1 sulfur, and 4 oxygens, all held together in some sort of unit. So these would be considered some sort of compound. Now, some materials, particularly ionic materials, like NaCl, don't exist as 1 sodium ion bound to 1 chlorine ion. And other materials like silicon SiO2, quartz, do not exist as discrete silicons and oxygens bound together. As we go spend more time in this, we'll start to talk about the properties of materials and being able to analyze these formula and tease out what type of behavior that they're going to undergo. But some molecules do exist, some compounds do exist as molecules, like CO2, where others exist as what we call network solids, like SiO2. Things like sodium and chlorine ionic compounds exist as aggregates of huge numbers of sodiums, completely balanced by huge number of chlorines. So they exist as huge aggregates of atoms. But the ratio is always 1 sodium to 1 chlorine. Now this again goes back to Dalton. The ratio, a number of atoms, the number of elements in a given compound is usually a small whole number ratio, 2 to 1 to 4. And we'll actually use this when we talk about empirical formulas later in the course. So these are chemical formula, and they represent atom ratios. And those atom ratios are either discrete molecules, groups of atoms held together, or as network solids, or ionic solids, which exist as groups of atoms that are all held together, usually by electrostatic interactions.